1.2, building cost of a heap. In this video, I will do the analysis, mathematical computation to estimate how much cost do we need to pay to build a heap. All right, so let's look at combine the cost of all heights. When we build a heap, I show you with one example, give an arbitrary array. So how do we go, level by level? So moving up. Yeah. So let's look at the cost for each level. Then we add up the cost of all the levels. Yeah. Cost of max heapify for all nodes of height h. One number, one height number, h, arbitrary. Yeah. Then from 1 through h. Yeah. 0, we do not need to build, right? Yeah, 0, nothing to build. Only the first level we start building our heap, height 1. Yeah. All right, so we know there are this many. Is it exactly this many? Remember the inequality I give you last time. Inequality. Yeah. Upper bound. So this is the upper bound. Yeah. Less than or equal to this many height h nodes, right? Height h nodes. So that's what we derived from the last video. Yeah. All right, so then the building cost for each such node. So one for each such node, after we do, swap operation, moving down to the leaf, you can see we need to pay this much big O of h cost. Each one we need to pay big O of h. Yeah, so that is each. But you have this many, so then multiplication. You do multiplication. That is for one level. All right? Can you accumulate the cost of all the levels? That's the formula. So we can write that formula directly. All right. Let's see. Heights from 1 to log of m floor function. Floor function. Yeah. The height. Okay. Yeah. Height of the root. Floor function. Yeah. Okay. Yeah. Leaf height 0 from height 0 to height floor function of log of n. Okay. Yeah. So then, yeah, skip because, yeah, that's height 0, right? That's h equals 0. Leaves h equals 0. Yeah. Nothing to build. No cost for the leaves. Yeah. So that's the reason we can skip them. Yeah. Summation formula. Summation. I hope, yeah. So you're familiar with this notation. Yeah. Pretty, commonly used. Yeah. All right. Each level, the cost is this much. Then adding up all the levels. So that is the expression. Yeah. Then because this ceiling function not very convenient to use. So we want to remove the ceiling function. We know the ceiling function is less than or equal to the part inside that bracket, yeah, ceiling brackets, okay, ceiling brackets plus 1. Yeah. So we make it larger, yeah, a little larger, yeah. So we use this expression. Okay. Then we split two terms inside the parentheses. So let's split them. The first part and the second part. Second part, this part should be easy, right? Yeah. Second part should be easy. Yeah. The first part, then it looks pretty complicated. Yeah. So let us separate these two terms. The second term, very easy, so let us do it first. The summation formula for second part big O of h, we just do summation inside big O. Okay, yeah. That's summation. This number approximately, floor function, we remove the floor function, so we make it a little larger. Yeah, actually we should put less than equal to, but here we use big O, right? Big O already it's a rough estimate, right? Rough estimate. Yeah. So we still use it, for convenience. Yeah. That expression. Okay, 1/2 log n plus 1. After simplification, because constant is not that important in asymptotic notation, so we skip it. Yeah. Then big O of log n squared. That's the second term. Log n squared, second term. Yeah. Now the key part. The first term is the key part. Second term, minor part. First term, major part. So let us estimate the main term, the first one. The first one, we can ignore the big O notation. We only look at the part inside big O. Okay, yeah. And here, the running index h is variable. H changes from I through floor function of log n. So h, we treat it as a variable. But n never changes during the summation, never changes. So we treat it as constant. So for that reason, we can factor n constant out of the summation to make the summation simpler. Yeah. All right. So next, we need to do this summation. Yeah. So that is much harder than what we have so far for the summations. What do we have? What do we have much easier than this one? Yeah. All right. So this one, so you can see actually two different series combined. We get this new series. So what two series? If you only look at the numerator part, so that is arithmetic series. If you just look at the denominator part, it's a geometric series. Now we put them together, combined, new series. How to find the summation. Yeah. All right. Yeah. Here you can see, in order to make the summation a little easier, we replace the upper bound of the summation index counting variable by infinity. We make it larger to infinity. Okay? Yeah. So we can add more terms. So we are very generous here, adding more terms. But still, we can control the enlarged estimate of the summation. Yeah. So we can easily handle that. Yeah. All right, so with this infinity upper bound, now we have this new series, S. We use S to represent the sum of the new series, infinite series. Yeah. So next, let us calculate the result of the series. All right. Calculate the summation. All right. When we start, we have this S representation. Okay? Yeah. To do the calculation here, we need to apply some trick. So otherwise, not very easy. Yeah. So you need to apply some smart trick. Yeah. But what kind of property can you observe in this infinite series? What kind of special property you can observe? So you can see the denominator is power of 2. That is very special. The denominator is power of 2. Yeah. Why so special? Yeah, because you can take advantage of that structure, power of 2 structure. How do you take advantage? Yeah. Very simple. Yeah. If you just multiply s by 2, then at each term you get cancellation, right? So, but you still, after the cancellation, you still get the power of 2 denominators, right? Still power of 2 denominators. So you can see, then if you compare 2 summation formulas, all in power of 2 denominators, then you can do cancellation easily. You can do cancellation easily. So this trick helps us explore the structure of the series. And our goal, we want to do as many cancellations as possible. So as a result, you get a simplified formula. Here, you can see when we do subtraction, the lower part subtract the upper part. When we do subtraction, look at the terms, the like terms, right? The like terms, yeah. Terms with the same denominator. The like terms, same of the denominator. Yeah. For example, in this big red circle, they have the same denominator. So we can do subtraction easily. Yeah. Similarly, the next pair of like terms, we combine them because they have the same denominator, and so on, all the way to the end, yeah, if there is end, because for infinite series there is no end, right? Yeah. But we know this pattern occurs all the way through the tail. Let's say the tail, not the end. All right. Yeah. After simplification, S can be written in, you can see it is a geometric series. After subtraction, you get a simple geometric series. The sum is 1. Then S is 1. Okay. S is 1. That's simple. That very simple. Okay. All right. Then our conclusion, to get a conclusion, build a heap, yeah, for the major term. Yeah. Then, because we take the n out, the remaining part, big O of, inside the parenthesis, it is 1. Yeah. After we take n out, big O inside the parenthesis, it is 1. Then we move that n back, so we get a big O of n. So that is the major term, major part. Remember, we also have a minor part, right? Yeah. Compared with the major part, minor part can be ignored. Yeah. Log n squared, comparing with the n, too small. It can be ignored. Okay? Yeah. This is dominant term. We only keep the dominant term. Yeah. So the answer is the building cost big O of n. So that's the answer. Yeah. And we complete this video. Yeah. All right. Yeah.